Assalamu alaikum. Bismillahir-Rahmanir-Rahim. I welcome you to the 26th lecture for the series of lectures on advanced computer architecture. Today, after a brief review of what we discussed last time, I will introduce to you the concept of cache in a memory and the principle of locality. Then we will also discuss the addressing techniques which are used for cache, and then we will discuss the transactions as they take place in random access memory versus the cache. As you know that the last time we reviewed the features of semiconductor memories such as the static random access memory, the dynamic random access memory, and then we also discussed some magnetic memories such as the disk, which is used for bulk data storage. While talking about these different types of memories or the storage medias, we noticed that the static RAM is the fastest type of memory, but it costs very high for information storage per byte. Therefore, the static RAM is usually used in small size, and it is always kept very close to the processor for high-speed operation. Whereas the dynamic random access memory is relatively slow, but at the same time it is also cheap per byte as compared to the static random access memory. Therefore, in any computing system design, the dynamic random access memory is used as the main memory of the system, and it holds both the instructions as well as the data which is directly accessed by the processor. Whereas the disk storage is slowest and cheapest. It's offer very low cost per byte, and it is usually used as a secondary storage to hold bulk of data as well as instructions. However, we also observed that the gap between the speed of dynamic random access memories and disk with respect to the speed of the processor is increasing very fast with time as compared to the gap of the speed of static RAM and the processor. Let us have a look onto the graph which we considered last time, which shows the plot for the CPU memory access time. Here you can notice that in the year 1980, the access time of dynamic RAM was about 800 nanoseconds, whereas the CPU cycle time was relatively higher, and it was about 1000 nanoseconds. That is, we can say the speed of dynamic random access memory was slightly higher than the speed of the processor. Thus, it offers a compatible storage media. Whereas in the year 2000, the access time was reduced to 90 nanoseconds, whereas at the same time, the CPU cycle time was also reduced to 1 nanosecond. That is, the dynamic RAM became 90 times slower than the CPU. So this shows that if the dynamic RAM is directly used with the processor, the overall performance of the system that will degrade. Whereas if we notice that the CPU and static RAM access time gap is still very small. Therefore, it suggests that either only the static RAM should be used as the main memory in a fast computer. But as we have already found that the static RAM is very expensive, therefore it will make the overall system exceptionally expensive. So the extremely expensive static RAM and the increasing gap between the speed of the dynamic RAM and CPU complements each other and suggest that the memory should be organized in an hierarchical form based on the concept of caching, where the concept of caching suggests that the data and instructions which are directly needed by the processor should be made available in the fastest memory. However, we can achieve this by making use of the principle of locality. So let us first of all discuss the concept of caching, and then we will talk about the principle of locality. The concept of caching states that a small, fastest, and most expensive storage be used as a staging area or a temporary place to store the frequently used subset of the data or instructions from relatively cheaper, larger, and slower memory. And at the same time, in order to avoid having to go to the main memory every time this information is needed, so this fundamental idea of caching basically gives rise to the development of memory hierarchy, where the devices of different type are placed at different levels. The faster, smaller, and expensive device at level K serves as a cache for the larger, slower, and cheaper device at a level K+1. And the programs tend to access the data or instructions at level K more often than to access the data or instructions are both at level K+1. Thus, the storage at level K+1 can be slower but larger and cheaper per bit. The net effect of this whole arrangement is that a large pool of memory that cost as much as the cheapest storage at the highest level, which is near the bottom in the hierarchy. It serves as the data or instructions at the rate of the fastest storage at the lowest level, that is, at the top level in the hierarchy. Here in this table, you can see different examples of caching in the hierarchy. For example, here you can see that the registers are used as a cache for smallest possible data storage, say a 4-byte word. It is placed inside the CPU, rather inside the data path. It has got 0 cycle latency and it is directly accessed by the compiler. Whereas the caches are made available at 2 different levels known as L1 cache and L2 cache. These caches are managed by hardware and they are usually placed on chip, that is, as part of the microprocessor chip. The virtual memory is cached as the main memory and it is managed by the hardware as well as the operating systems. The other types of caches are the buffer cache, network buffer cache, browser cache, and web cache. These are usually used at the web server browsing and the web proxy servers. However, the use of these caches is where there is a very high latency. Now, with this much introduction about the concept of caching, let me give you the basic concept of the locality. The principle of locality states that programs access a relatively small portion of the address space at any instant of time. This is the main principle. So this is basically what also happens in a real life. For example, we know that we have a lot of friends, but at any given time, most of us can keep in touch with a small group of these friends. So this means that out of a large pool of our friends, at a particular instant of time, only a small group is being contacted. Another example of the locality is the use of the library. We know that when we go to the library, we find as if there are hundreds or thousands of books which have been placed in particular order in different shelves in the library. However, suppose you are given an assignment to consult books only in, say, 2 subject areas like electronics and computers. When you will go to the library, you will prefer to pick most needed books from the big collection in the field of electronics and computers, and you would like to place those books very close to you on your table where you want to sit and study. So this means that out of a very big collection, only a small number of books are consulted at a particular instant of time. So this shows that we always want to locate or to place these books which are needed during our studies very close to us. So considering this particular mode of locality, we can say that locality can be classified into two different types, namely the temporal locality and spatial locality. Let us talk about the temporal locality first. The temporal locality is the locality in time which says that if an item is referenced at a particular instant of time, it will tend to be referenced again very soon. For example, if you studied the first book in electronics from your book very close to you, and then you switch on to the book on computer, it is a very big chance that in the next moment you may have to consult the book on electronics again. Or from our example of friends, we can say that if you just talk to one of your friends, it is likely that you will talk to him or to her again soon. The spatial locality, on the other hand, is the locality in space. The concept of spatial locality states that if an item is referenced, then the items whose addresses are close to this particular item will tend to be referenced soon. Here we will once again, using our same analogy of friends, we can say that usually we can divide our friends into different groups, such as the friends from high school, the friends from work, or the friends from neighbors. Let us say you just talk to one of your friends from the high school, and he may utter something like this: "So did you hear that Mr. So-and-so has just won the lottery?" And then at once you would like to give a call to your other friend to congratulate him for winning the lottery. Here you just talk to one friend from your high school days, and as a result you end up talking with another friend from the high school days. Similarly, from our library example, we can say that while consulting a book on electronics, you might be referenced to another book on electronics which must be located on your desk. That is, it should be located at the same space. So this is what do we mean by the spatial locality. So now we will take up the examples of execution of programs to explain the concept of locality. As you know that during the course of execution of a program, memory references tend to cluster. For example, loops refer to the small portion of memory repeatedly. For example, if there is a while loop, then all instructions within this while loop, they will be referred repeatedly. So, a well-written program tends to reuse the data as well as instructions which are either near those they have been used recently or that were recently referenced themselves. So, summarizing the concept of locality, we can say that the special locality is one where the items with nearby addresses, that is, the items nearby in space, they are to be located at the same level because they tend to be referenced close together in time. And the temporal locality is one where the recently referenced items, that is, the items referred in time very close to each other, be placed at the same memory level as they are likely to be referenced in the near future again. In order to understand this concept, we can see the example of this small program. Here in this example program, let us consider that we want to add n elements of an array. So, to see how the locality principle is used for the instructions and the data references, we can see that for the special locality, all the array elements, that is AI, or the data elements we can say, are referenced in succession at each loop iteration. So, all the array elements be located at the same level. And also, all the instructions of the loop are referenced repeatedly in sequence. Therefore, they are to be located at the same level. So, this means that all instructions of the loop as well as the all data which is to be used within a loop, they are to be placed at the same level. Whereas, with reference to the same example, for the temporal locality, you can see that the data sum is referenced in each iteration. That is, recently referenced data is referenced in each iteration. And also, the instructions of the loop, that is, to find the sum of the elements of the memory, they cycle through the loop repeatedly. Now, with this much introduction about the concept of locality, let us discuss how the memory hierarchy works based on the principle of locality. Here, we can say that in order to take advantages of the temporal locality, that is, the locality in time, the memory hierarchy should keep the more recently accessed data items closer to the processor because the chances are that the processor will access them again soon. In order to take advantage of the special locality, not only do we move the item that has just been accessed closer to the processor, but we also move the data items that are adjacent to it. With this much introduction to the concept of caching and the principle of locality, let us discuss the design of cache devices and the cache organization. Cache device is a small static random access memory which is made directly accessible to the processor as well as to the larger dynamic random access memory. The dynamic random access memory is accessible by the cache as well as by the user or the programmer. And the dynamic random access memory is placed at the next higher level as the main memory in the memory hierarchy. Similarly, further larger storages such as disk that is placed away from the main memory, and this way we can use different types of memory as cache for the memory at the next higher level. For example, the register files are used as the cache for the data path, whereas level 1, level 2 caches are used for the processor and for the main memory, whereas the main memory can be used as a cache for the secondary storage, and so on. Considering this, let us have a look onto the cache organization. A cache sits between the normal main memory and the CPU as the data and instruction caches, and it may be located either onto the CPU chip or a separate module just very close to the CPU. Moreover, the data transfer between the cache and the CPU and between the cache and the main memory is performed by a hardware which is available with the cache and is usually known as the cache controller. And the cache and main memory is organized in equal sized blocks. This means that the total space available in the cache as well as the space available in the main memory, they are divided into small logical segments known as blocks. And the data transfer between the CPU and caches takes place as the word transfer, and the data transfer between the cache and the main memory takes place as the block transfer. This actually means that when the CPU has to transfer either an instruction or data to the cache, or it has to fetch an instruction or the data from the cache, it is fetched in the form of an instruction word or a data word. Whereas if some information is to be transferred between the cache and the main memory, then this transfer takes place as a block transfer. Now let us have a look onto this diagram and understand how caching in memory hierarchy is performed. Here you can see that the lower section shows a larger, slower, cheaper storage at a level k plus 1, and this memory is partitioned into 16 blocks, whereas a smaller, faster, and more expensive device at level K caches a subset of blocks. In this particular example, a subset is of 4 blocks, and it caches the information from level K plus 1. And the data is copied between level K and level K plus 1 in the form of block size units. Now, before we proceed further onto the design of the cache, let us first of all understand how the blocks in the main memory and the blocks in the cache, they are placed at different locations. This particular concept is referred to as the concept of the placement. For the placement purposes, basically we have to understand how different blocks are located in the main memory, and they are addressed in the main memory, and the corresponding blocks in the cache are being addressed. For this purpose, let us consider this example of the main memory at level K plus 1, which has got 16 blocks, and these 16 blocks can be addressed by a 4-bit code, which is, say, written over here as XXYY. Whereas the 4 blocks of the cache at level K, they are addressed by a 2-bit code, because a 2-bit code can be used to address 4 different locations. Here you can note that the address of the main memory and the addresses of the cache blocks, they have got a direct relationship amongst themselves. That is, all blocks in the level K plus 1, which are shown in one column, they are placed at a corresponding position in one block of the level K memory. For example, at the block position 00 in the level K cache, the blocks from address 0 or 4 or 8 or 12 can be located. Similarly, at location 01 in the level K cache, the blocks from K plus 1 located at 1, 5, 9 or 13 can be located. So this shows that at one particular location in the cache, number of blocks from the main memory or from the higher level memory can be placed or located. So this means that in order to use a cache, CPU requests the contents of the main memory. For example, CPU generates the address, say, 0001. Whereas the cache controller checks the cache block in the column corresponding to 01 for this purpose to get this data from the cache. If the required information is available in the cache, then the CPU fetches this information from the cache. This means it is a very fast transfer. Whereas if it is not present in the cache, then a block read is required from the main memory to the cache, and then the required word or information is delivered from the cache to the CPU. Now, before we proceed further, let us discuss a few terms which are useful in order to understand the concept of caching. When the data the processor wants to access appears in the cache, or say in the upper level memory, then we call this a hit operation, and the fraction of memory accesses that are found in the upper level in given time is referred to as the hit rate, whereas the time required to access the upper level is referred to as the hit time. This time consists of the RAM access time and the time to determine if this is a hit operation or not. Whereas if the data needed by the processor is not found in the upper level memory and it has to be retrieved from a block in the next level memory, that is, in case of cache and main memory, if it is not found in cache and it has to be retrieved from the main memory, then we call this a miss operation. The miss rate can be determined as 1 minus the hit rate, whereas whenever there is a miss, we have to pay some penalty in terms of the time, and this is consisting of the time to replace a block in the upper level and to deliver the block to the processor. However, here we can say that in order to have a good design, the hit time must be very, very small as compared to the miss penalty. Otherwise, there is no need to use a memory hierarchy. So now let us have a look onto this cache and main memory diagram again and see how we can define the hit operation and the miss operation. For example, over here, you can see that if the CPU needs object D, which is, say, stored in some block D, in this particular case, let us assume that it is stored in block number 14 in the level K plus 1 memory, and the corresponding block should be available at position 2 of the cache at level K. When the CPU makes a request and it finds the block B, or say in this particular example, the block 14 in the cache at level k, we call this operation a hit operation. Whereas if a program needs a block which is stored in some block, say in this particular example at block 12 at level k plus 1, then the block 12 from k plus 1, if it is not at level k, that is, it is not available in the cache, then we will call this operation a cache miss operation. Hence, at this stage, the level k cache must fetch it from the level k plus 1 and then transfer this object to the CPU. However, note that if the level k cache is full and the required object is not available in the cache, then this particular block must be replaced by the required block. So, in order to replace this by a new block, which particular block is to be moved from here is referred to as the victim block. The victim basically depends upon the design of the cache, which defines the relationship of the cache addresses with the higher level memory addresses. For example, it may be a directly addressed cache, or it may be some other type of addressing technique which we will discuss later on. Furthermore, it depends upon the placement policy that determines where can the new block go, and it also depends upon the replacement policy that defines which block should be evicted, where the new block should come. Now, before we proceed further to discuss the design of cache memories, let us see what are different types of misses or miss operations which can take place. The miss can be classified into three different types, namely the cold miss. Cold miss is also sometimes known as the compulsory miss, which occurs when the cache is empty. Usually, it occurs when we initially switch on the system and the cache is initially empty. Now, if CPU needs some data or instruction from the cache, it will definitely miss. The other type of miss is referred to as the capacity miss. The capacity miss occurs when the set of active cache blocks, that is the working set, is larger than the cache itself. So, in this case, there is a shortage of capacity in the cache itself. The third type of miss is known as conflict miss. It occurs when the level k cache is large enough, but multiple data objects are mapped to the same level k block. For example, if the placement policy is based on the direct addressing, then referring to block number 0 or block number 8 in a sequence, that is 0, 8, 0, 8 and so on, then a miss will occur every time a block determined by 8 modulus 4, which results in a value 0, is accessed at the level k memory, as both the blocks 0 as well as block 8 of the level k plus 1 memory are always placed at the same location, that is 0, 0 in our earlier example at the level k. So with this much introduction about the terminology, let us discuss the design of a cache. We have observed that more than one blocks from the k plus 1 memory, say from the main memory, having n blocks may be placed at the same location given by n modulus m in the level k memory, having m blocks. Hence, in order to avoid the conflict maze and in order to overcome this problem, a tag must be associated with each block at level k cache in order to identify its position in the level k plus 1 memory. Now, in order to understand the design of a cache, let us consider a realistic example. Let us assume that our main memory is of 4 gigabyte, which means that it can be addressed by a 32-bit address. Whereas, assume that we want to use a 1K byte direct addressed cache with a block size of 32 bytes. So, as you can see from this block diagram, for each block of 32 byte, a tag is associated, and the address translation from the address of the main memory to the address of the cache is determined such that the 32-bit address generated by the CPU is divided into 3 blocks, where the 5 least significant bits of the address in the first section, they address each byte in every block. Since the cache is of 1K byte, therefore any byte of the cache can be addressed by a 10-bit address. And as the main memory address is of 32 bits, therefore 32 minus 10, that is 22 bits long tag is to be associated with each block of the memory. And the middle 5 bits in this example, that is the bit 5 through 9, they are used to index any block of the cache. So this shows that the design of a direct address memory is very simple and its addressing is also simple. However, it has got number of pros and cons in order to use this memory efficiently. So far, we have been talking about the concept of the cache, concept of locality, and then the basics of the design of a direct map cache. We will continue with this discussion next time, and we will talk about what are the limitations in the design of the cache, how we determine the block size, and how it affects the overall performance of the system. With this much discussion today, I say you Allah Hafiz. Thank you very much.